Today we're going to start looking at TDD in a new language. We're going to look at testing in Go. Hi, I'm Mark Bradley and welcome to Testing All the Things, a screencast in which we use live coding to demonstrate different types of testing tools and techniques. In today's episode, we're going to look at testing in Go. We're going to continue using Uncle Bob's 3 rules of TDD. The Go programming language comes with its own testing framework. In today's episode, we are just going to use the features provided in Go's core library. Let's look at the code.
As I said in the introduction to this video, we are going to follow Uncle Bob's 3 rules of TDD whilst we create this stack. Uncle Bob's 3 rules of test-driven development are: write no production code except to pass a failing test. Write only enough of a test to demonstrate a failure. This includes compilation errors. And finally, write only enough production code to make the test pass. For this last rule, you are looking to use the simplest implementation to make that test pass. Now we know the rules that we're going to follow during this video, let's start implementing our stack. The first thing we want to do is for our stack to tell us whether it is empty or not. So let's create some tests to drive out that functionality. So if we create a new test, let's call it empty. And let's start writing the test code. So S E. So we can quickly fix the first error by importing that. Okay, now it's saying unresolved reference new stack. So we need to come over here and fix that before we can carry on following Uncle Bob's rules. So function new stack. There we go. Okay, we've still got this red squiggly line. So new stack does not return a value, but we're definitely expecting it to in our test. So let's get that working as well. So we need to return a stack, and we need to know what a stack is. So we can create an empty struct for now. So let's do that. So type stack struct, nothing inside it, but now we can return one. So return stack. There we go. Okay, cool. So now our only error is the test error, which is fine because we're going to carry on writing our test. So Go offers, Go comes with a testing framework as part of the language. This test here is part of the Go language, but the language doesn't come with any assertion library. So to do assertions without bringing in any external libraries, you just use if statement. So we do if s.empty is does not equal true. Let's make it clear. So if it does not equal true, there we go. Okay, now we need to stop again because we now need a function on our stack called empty. So let's go and add that. We got method. So stack receiver s. Go. So we want this to be called empty. Takes no parameters, but returns a boolean according to our thing. It's just there we go. Okay. So this needs to return a boolean. So let's for it to compile. So return. Let's just put it false. So it returns something. Save. Okay. Bad me. Forgot the case. There we go. Empty. There we go. Now we can call the function. Excellent. Okay, so if empty does not equal true, then we need to fail our test. And the way we do this is to simply do t dot error, and we'll use error f so we can write something out. Actually, probably just going to use t. There's just an error in this one. So stack was not empty. There we go. Okay, and there's our first test written, so now we can actually run the test. So run the test. Okay, so the test failed because the stack was not empty. So, well, that's quite simple. To make the code compile, we returned this hard-coded false. And to make the test pass now, we can just switch this false out to true. That's the easiest thing we can do to make this test pass. It's the only thing that our test requires us to do is currently, if we call is empty, it should return true. There's nothing else to do at this moment. So let's save that and run our tests again. And we're green. So currently our stack's nicely implemented and we can move on to the next bit. So now we need to start putting things onto our stack to check that it becomes not empty once we've added things to our stack. So we'll create a new test. Let's call it not empty. Like so. Okay, that's nice and simple. So let's call the same again. So let's bring this in. So we've got a stack. We need to call s.add to it. Now, to make things simple for this implementation, we're just going to make a stack of strings. So our add function takes a string. Let's call it, let's use name, so let's call it Bob, as we're using Bob's rules. There we go. Okay, so we've added something to it. This is now red, it won't compile because this function doesn't exist. So we can go over here and add that to make it compile. Method, there we go. So stack, and we'll just call S again. Name is add, and parameter, it does take one, which is, let's say, value, which is a string. Cool, and it returns nothing. So, oh no, it returns nothing. Better. Cool. Okay, so we're all back and everything should compile. So now we can write our assertion. So if s.empty does not equal false, then t.error stack was empty. Okay, excellent. Okay, so run our tests, and we've got a failure again. Line 22, stack was empty. Well, it's quite obvious now why the stack is empty, because we're just returning a hard-coded true. So we now need to look for the easiest way to solve this failure. We can't now swap it out to false and hard-code it to false because that will fail the first test. We need both of our tests to pass. So what's the easiest way we could make this happen? Well, if we put a variable on our stack that kind of holds whether it's empty or not, that would probably work. So if we do is empty and make that a boolean, save, and then when we create a new one, it's empty, so we'll say it's true here. Yep, true, save, and now we can return s.is empty here, save. That will work, so that will return true for the first one. And now if we use s.is empty equals, change it to false here when we do an add, save. Okay, so that should now pass both of our tests. So let's run the test and have a look to make sure. Yep, typo there. There we go, cool. There we go. So stack's now changing. There we go. So as we add, we just mark that the stack is now not empty. And that's all the code that our test requires us to write at this point. So let's look at adding some more functionality. So now that we know when a stack is empty and when it's not empty. We now want to move on and look at the size of the stack. So start with the simplest test. So we'll do a new test, empty size 0. Let's just check size 0 actually. Test size 0. Okay, there we go. So we'll bring down and create an empty stack inside our test. Excellent, there we are. Okay, so if our stack size does not equal 0, then we want to do something. So we need to stop now because obviously we now need a size method over on this side, so we'll add that. Okay, stack s size doesn't take any parameters, but returns an int. Okay. Okay. Right. So still erroring out because we're not returning anything. So if we return -1, so we'll never have a stack smaller than that. So that'll make our code compile. Okay. Now we can continue writing our test. So this time we want to probably provide a little bit more feedback when we error out. So we've got there's two styles of doing this. We'll use one for the first and then we'll change it in the second. So we can, if we do t.error here, we can just, we can use error f, sorry. So we can do something like expected 0 elements found. And then we go %d, that's right, s dot size. There we go. Okay, cool. So there's our implementation, so that should now run. So if we run our tests, okay, there we go. So there's our error for this test now. So we expected 0 elements, but we found -1. That's because of our hard coding. So we can go back and quite simply fix that by changing the hard coding from a -1 to a 0. And hopefully our test should pass. So save. Okay, excellent. There we go. Tests are passing. So we can now add one more test to our next test. So we can test new test, and we'll test the size of where we've added 1. So size 1. Okay, and we'll take the same again. So we'll create a stack, and we'll add a value of Bob, and then we want to do if s size does not equal 1, then we want to error. Now I said there's different styles and different ways of doing this. So you've got this first one where you just keep it as a single line, which is quite nice, or another way to do it is to kind of be a little bit more verbose in the output. So you can do something like this. So t.error incorrect size, and then we can do t.info t.log f, that's what I was looking for, not info, there we go. So expected 1, and then t.log f. Oh, that doesn't actually need to be a log f, does it? That first one. So t.log and t.log f actual d s dot size. Save. Okay, now let's run this. And we've got a failure again, so let's have a look. Okay, there we go. So the output's a little bit more verbose. It depends on kind of what you want to do. Either style is quite nice. I've seen both used. This style is much more useful for kind of if what you're comparing is a little bit more difficult to look at. If you're creating some kind of, if you're looking for kind of a formatted string in some way, then kind of printing them out above each one above the other makes it a little bit easier. It's personal preference. So there we go. So there's that one, but this is failing because we expected 1 and we actually got 0. So what's the easiest way we can make this pass? Well, we have this empty thing at the moment, so let's use the empty. So if return, how about we do this? So if not s dot is empty, so if it's not empty, oh, we can just use that actually. Return 1, else we return 0. That'll make it pass. There we go. Brilliant. There we go. Another passing test. So obviously we're not there with the implementation of our size function yet. So let's drive it out with a further test. So we'll skip 2 and we'll add a test for 3. So size 3. Okay. Bob, Dave and Sarah, there we go. Okay, so we'll go back to our kind of shorter style for this one. So if s.size does not equal 3, then t.error f, there we go, error t.error f, what do we say? Yeah, expected, let's just do 3, found, and then percent %d, no, d, and that is s.size. Okay, right, so we'll run that test, and lo and behold, it fails. So we expected 3, we found 1. Well, obviously this implementation doesn't work past 1 and 0, so we need to look at a new way of doing it. So it looks like we need to add yet another variable to our stack. So let's look at that. So we've got this boolean. Well, let's keep track of the size maybe as an int. There we go. So we need to add the size in here. So starts at size 0. There we go. And now we can just return s.size. There we go. Lovely. Now, obviously we need that to increment, so as well as setting empty to false, we can do s.size and just increment that like that. There we go, lovely. So hopefully now all of our tests should pass. And they do, all green, brilliant. So let's have a look at our code. So the test-driven development cycle is red for writing a failing test, green when you've got all your tests passing, and then the next step is your refactor stage. So it's red, green, refactor. Now, you should only refactor whilst you're at green, which we're at. So let's look at whether there's any improvements we can make to our code internally that kind of make things a little bit cleaner. So during a refactor stage, we're not looking at making any changes to the external functionality. So the interface should stay exactly the same. Refactoring is just about changing the internals and cleaning up the code and how it works. Now, we've now got this is empty and this size. Now, one thing we do know is that a stack with a size of 0 is an empty stack. So we could remove our is empty variable and just make use of the size in the empty functionality. So if we do return size equals 0, there we go. Okay, And if we run our tests again, we're all green. Excellent. So now, really, we don't need to change this flag here at all. If we save that and run it again, okay, this test's still passing. So now I think we can actually completely remove the field and remove setting the field, save, and if we run all our tests, we're green. So that's a really nice, neat little refactor. Okay. So now that we've got our size functionality working and our empty functionality working, it's now time to start testing the pop functionality of our stack. So we can start with a nice simple test to pop a single thing off of a single stack. So create a new test, let's call it pop1. Okay, there we go. So we can create a quick stack. Okay, so we need to pop that value off, so we need to store it in a variable quickly. So v equals s dot pop. Okay, so red, so we need to go over to the right hand side to fix things. So new method, go stack s pop, takes no parameters and returns a string. Okay, there we go. Okay, so the code will not compile just yet because we need to return something, so we can return an empty string to make it compile. Now we can go back to writing our test. So if v does not equal Bob, then t dot error f expected Bob found s, and that's value v. There we go. Okay, so our test is ready to roll. So let's write the test, run test, and we're failing. And we're failing because we expected Bob, but we found an empty string. So what's the easiest thing to do to make this pass? Well, we'll just write the word Bob there. There we go, done. Okay. Brilliant. So that is the pop for one working. But I think we're missing an assertion here now. When we pop something off of the stack, it should have disappeared off the stack. So we need to also check the size. So let's do a quick if s dot size does not equal 0. Or we can check it's empty, so it's either or. So we'll check just for the size, because that's probably the easiest one. So we can do t dot error f expected size 0 found %d. So found %d, and that is s dot size. There we go. So two assertions to check that the full functionality of our pop function works. So run it. It's failing because so we expected size to be 0, but we found 1. So how can we fix that? Well, that's a reasonably easy fix now. We can just do s.size and just decrement the size variable by 1. So there we go. Now if we run our test, excellent, it's all passing. Lovely. Okay, so we can go on to our next test. So So we want to now pop off a stack that has more than one value on it. So let's now start making that work. So we'll create a test to do pop a 2 stack. Okay, so let's just borrow this code again. So we've added Bob, and now we're going to add Alice. Okay, so the idea of stack is that the last thing onto the stack should be the first thing off of the stack. So in this test, we want the value of v to be Alice. That was the last added value. So t dot error f. So we expected Alice, but we found send s and give it the value of v. Okay, cool. Save. So now we can run this. Okie dokie. So run. And oh, it's failing because we expected Alice, but we found Bob. Oh dear. Right, okay, so we're returning this hard-coded value here, so that does need to change. Let's have a little think. Right, well, if we, here we go. So to make this test pass that we've got in front of us, we can do this. So we can do value is a string. When we construct it, we can just give it an empty string. And then we can return, or when we add, we can do s.value equals the value that comes in. And then we can return s.value. There we go. Okay, I think that should work. So let's run the test again. Yes, it does. Beautiful. There's everything we need to make that test pass so far. So let's have a look. Okay, well, okay. So we know that's not going to be the final implementation, and our test is not fully written yet, because obviously we've now got another value that we can pop off of our stack to check the full functionality of our stack. So v2 equals the next pop. Cool. And let's speed things up a little. Copy paste. There we go. So this should be Bob. We're expecting Bob, and we want the value of v2 and v2. There we go. Lovely. Cool. So save that, and we can run our test again. And shock horror, it's a failure. There we go. Okay, so we expected Bob, but we found Alice. And the reason that's happening is because really we're now only storing the last value that was added to our stack. So we need to solve that problem. Well, so it sounds like we're starting to need some kind of internal data structure that's going to hold more than one value. So what can we use? Well, well, we've got this value already. Let's maybe make use of that. Let's call it values. Let's make it, instead of just a single string, let's make it so values, instead of a single string, we can make it a slice. There we go. So there we go. So now when we construct a new stack here, we can do, we can make a string, lowercase, not in Java anymore. And let's just give it a size of 5. That'll make our test pass. Okay, save. Get it right. Values make string. What would number of it? Wrong way around here. Sorry. There we go. There we go. That's a bit better. Brackets to the other side. There we go. So give it a value of 5. Now we need to start adding things into our slice here. So what we can do, we can use the size variable of our struct. So if we do s.size, cool, like that, and if we whack the incrementation, incrementation below, then there we go. So now the first one will be, and that needs to be called values. So now if we do that, so when we add our first one, the size is 0, so it goes into the first element of the slice, and then we increment, and then we come back round for adding the second, and it goes into the 1 value, so that works perfectly. Okay, and now if we go down to our pop, so now we're quite lucky because we're already decrementing, so because our last value will be in the position of size -1, so we don't need to do any trickery. We can just return the size that it is as it pops off. Save. Okay, and we can run our tests. Oh, typo, values, save. Let's try again, shall we? Run. Cool, and we are all green. So we now have a fully working stack in Go. Well, kind of, there's some things we need to go and solve, like the fact that we construct this at a value of 5 for a size of 5. We might want to look at that for later on. And also, we're not handling whether when we pop off of a, if we try to pop on an empty stack, whether sort of that's, there's a few ways of looking at it. We could either just return an empty string, which is probably not the best thing. We want to look at starting return errors. But for a quick, simple demonstration of the testing ability that comes with Go as a programming language, I think that's quite a nice little demonstration. So it writes quite long tests because of the lack of the assertion library, but it's all quite nice, neat, and readable. What we will do, though, in upcoming videos is we will look at different assertion libraries and different testing tools that there are out there for us to use in Go. But for tonight, that is everything. Thank you very much.
Thank you for watching this episode of Testing All the Things. I hope you found it useful. If you enjoyed it, please rate the video and subscribe to the channel. If you did not, please leave constructive feedback in the comments. If you would like to suggest something you would like covered in a future episode, please leave a comment as well. I'm Mark Bradley. You can follow me on Twitter at Braddle, or if you're just interested in all things testing, then follow at TestingAllThe.